I have not changed the title, it's just an abbreviation of what I would like to tell you today. And I will summarize one of the recent measurements we have done in the subpolar North Atlantic, and there are also contributions of my co-workers, which are also named here. So to give a more broader perspective, if you look for ocean and climate change, you usually, that is one thing in the ocean, go where the big signal is. That's what you would like to do. And one of on the left-hand side, you see the part of the meridional overturning circulation. Both my speakers before have also talked about. And on the left side, you see from several climate models, you see under a greenhouse scenario, you see what the meridional overturning circulation in the Atlantic is doing at about 30 north. And if we just summarize over everything, it seems that in the future, the AMOC will close down by about 30%. And what does this reduction, is that interesting, or is it just a local, let's say something which oceanographers are really keen on, but nobody else? Then we just look what's happening if we not have the greenhouse gas, but this is just a high-resolution model where the AMOC was reduced by about 30%, and what is shown here are the sea level change, only by circulation. There is no greenhouse gas, no warming of the ocean included. It's just sea level by changes in the circulation, and you see this is the ORCAM model, which is run in GEOMA. And in Kiel, so you see there is about, let's say in a maximum, about 20 centimeters height, which you have to add by the change of the circulation, and you have to add that also, which comes from thermal expansion. Another thing, it was also from climate model. This was published by Stauffer et al. Some years ago, where you see the change in the atmospheric temperature after cessation of the AMOC. You just only reduce by 30%, but you just shut it down by, and you see that there is a strong cooling in the western hemisphere, and there's a strong cooling, especially in the Atlantic. And if we look for the climate models with greenhouse gases in the future, and this what's shown here is the temperature change we expect in the next 100 years, and you see there is a temperature minimum change in the Atlantic, and also which also affects our part where you live in. And of course, this is the effect of the warming, and also the cooling from the changes in your circulation. Having said that, there is a problem with the subpolar North Atlantic. What we see there is, we think that, if we go back to it, here, that the changes of the AMOC are somehow related also to the changes, and we have seen that in the subpolar North Atlantic, where these deep waters are formed, and I don't want to go into detail now, but what we see is that we also have a lot of variability, which is natural. It's an interannual, it's decadal, it's longer timescales, and they, at the moment, dominate the observations. And most of our time series are very, very short compared to all this variability we see, and so it's very difficult to separate the trend, which we probably also see now from the global warming, from the variability which is there. And of course, to understand, we need to understand that variability, and you also, of course, need to measure it. I want to separate my talk and in several of those topics. The first is I want to show you what we know at the moment about what the changes in the Labrador seawater formation rates are. And then from these changes, go to the subpolar gyre and tell you how the circulation pattern and also probably the strength is related to the North Atlantic oscillation. And I will show you some transport and changes in water masses and how this is related somehow to the AMOC and also to the Labrador seawater formation changes. And from that, I will go to the Western Basin, That's also following my motto, go where the big signal is. There is a lot of circulation going on in the Western Basin, and we hope we see also there a lot of changes. And we also then go to the, I want to present to you a full tracer set and tell you about the pathways of the deep water in the North Atlantic. And then, of course, make a short outlook about what the future observations will be. So this is the area we are looking at for the moment. So this is the subpolar North Atlantic, and this greenish is part, this is the Labrador seawater. Sea means convections, which most of it is formed in the Labrador Sea, and then it spreads into the subtropics and also spreads to the east. And you see it's closely related to the white arrow, which is the North Atlantic current. Yeah, and it's also the North Atlantic current crosses here and it crosses into this into the Eastern Atlantic and then even goes further to the north. This more bluish part, this is the Denmark Strait, and Iceland's called an overflow water, which also is part of this deep western boundary current, and these were also these lower North Atlantic deep water Harry was talking about in the last talk. So now we go into the Labrador Sea, here in this area, and I show you here a temperature and a salinity time series starting from 1970 to 2009 from the central area of the Labrador Sea. And we just look at the temperature. You see, we have not as high, we have relatively high temperatures in the upper 2,000 meters, so this is Labrador seawater. And then in the mid-90s, we know that there was this intense convection going on in the Labrador Sea, which makes the water cold and also saline. And afterwards, after the cessation of this strong, intense convection, we have some convection going on. There was Labrador seawater formed, but it has a different density. And as a proxy about how intense or how strong convection is, one usually for longer time series takes the thickness of the Labrador seawater layers. And here I have split it let's say, in the upper Labrador seawater, which is the bluish curve, and the deep Labrador seawater, which is the reddish curve. And you see that in this mid-90s, where we also have this very cold water, we have here a thickness of this layer of more than 2,000 meters. And what I call upper Labrador seawater was almost negligible at that time. But if you now go, if we move on with time, even now the upper Labrador seawater is much is thicker than the deep Labrador seawater. So there was an increase of this upper Labrador seawater, and we have a decrease of the deep part over the last 15 years. We are looking to get not only a proxy, but to use CFCs to actually calculate formation rates, and therefore we need inventories. And in the talk by Edouard, there was also mentioned that these transient tracers, which are introduced into the surface of the ocean, are often and frequently used to follow water masses, and we can also use them to calculate formation rates. So, and I only want to show you one example. One is 1997 and then 2005, and then go directly to the results. So this is the inventory in the deep Labrador seawater in 1997. That was after we had these very intense convections. And you see there is a lot, this reddish means there is a lot of these CFCs in the Labrador seawater. And one also sees the spreading into the Irminger Sea, and there's also some hints that in the beginning of the 90s there also might be some Labrador seawater formed in the Irminger Sea. And we have a spreading to the south in Newfoundland Basin, and there is also tongue going into the eastern Atlantic. And this upper Labrador seawater, as I told you, was always minor. It was very thin and didn't have much inventory. And this is totally different to the observations we made in 2005. There you see most of that of this high, it's the same color scale, it's the same scale. So here, this water has moved away. It's not there anymore. But on the other hand, because this upper Labrador was still formed, you still got introduced of CFCs inside it, and so we really got here a higher inventory than we had in 1997. And if you use these to calculate formation rates, this is, we started this time series in 1997, and you see we had about, I just add up all these Labrador seawater modes. But in the beginning, we had a lot of deep Labrador seawater formed. It's about 7 to 8 sverdrups. And then it's decreasing until about 2005, where we had only about 2 of those. But this was only, this formation here was upper Labrador seawater and no deep one. And there was, here we don't have a biannual. It's only biannually possible because we don't have enough sufficient measurements to do it from year-to-year basis. And here, by some of the technical problems we had with the ship engines, we even have to spread to a 3-year mean. And we hope by some, we are thinking about and calculating if we could split that up anymore. But at the moment, we have to stick with that, and there was an increase again. But we know that it was only one winter where these, where also the deep Labrador seawater was formed, but in the other winters, it just went back to normal. And on the upper part, you see the North Atlantic Oscillation Index, which is, let's say, the pressure difference between the Icelandic low and the Azores high. And in the beginning here, we have this very high NRO, which also leads to these, we also see here the rest of these very huge, very large formation rates. And then it somehow went down, and we have a phase here with very low NAO, and there was a little bit of increase, and it goes down. The other curve which is shown here is this Baroclinic Transport Index, which is an index about the strength of the combined subpolar and subtropical gyre, which was from Curry and McCartney, which we just updated for this part. But I will talk about, I would like to talk today only about the subpolar gyre, so I skip that and we come back to that later. We can also use floats to look for the spreading and a circulation of water masses. And these are trajectory of Argo floats, which are either in 700 meters or in 1500 meters. And you see they have, the black dot is where they have been launched. And then they spread, what you see, they go into the Irminger Sea, they spread, they are only, the launching is either in the Labrador Sea or along the western boundary current, or they spread into the eastern Atlantic, and there are also some which leave the subpolar gyre, and we will talk about that also later. And here you see the locations where those floats cross the East Atlantic. So a lot of them cross into the Eastern Atlantic, and we will go into that also a little bit later. We can also take the Labrador seawater and a sort of an estimate of how long it takes to reach this mid-Atlantic ridge from the western boundary current by following anomalies. This is not CFCs, it's just salinity anomalies. You remember that if you have, when we had these years of very intense convection, we had a lot of, the Labrador seawater was fresh, and afterwards it got more saline. And by the spreading of those Labrador Sea, of those anomalies to the mid-Atlantic ridge, we can even have some sort of a time scale, how long it takes until it reaches the mid-Atlantic ridge. And there was a paper by Kike et al. In 2009 who combined hydrographic sections at 48 and north and surroundings with moorings which were set by Koltermann from the BSA Chernabock. Okay, now I showed you that we have seen changes in the formation of Labrador seawater, which is now part of the circulation in the subpolar gyre. And I want now to show you what the ideas is, how the NAO and the subpolar gyres are related. So on the left side, we have high NAO state, and in the right side, we have the low NAO state. And these are figures by Sarafanov and Blindheim. And here, when we have high NAO, we know there is a high convection. There is convection in the Labrador Sea, maybe also in the Irminger Sea, so a lot of Labrador Sea water is formed. And we have a lot of cold water here, so the subpolar gyre is extending to the east. And the water from the subtropical gyre, there is some of it is of course also entering into the eastern basin and is taking part in the subpolar gyre, but not as much as compared when we have the NAO minus state, where the subpolar gyre is shrinking from to the west. So then there is more of the subtropical gyre water is entering the eastern Atlantic, so this is getting more saline compared to this, and it's also getting warmer compared to this, and it somehow also counteracts this. Where it's different, and we can see that also from hydrographic data how different that is. I will come into that in a moment. That also has implications further north. That's what's shown here. If there is a compared in the NAO plus state, we think that there is more from, there is water. There is inflow also, of course, of this warm and saline water into the Nordic seas and also into the Arctic. But if you compare those two sketches from Blindheim, you see that the ways how it's doing and how much of it is in the Nordic seas and going into the Arctic is different between those two states. These are just schematics. What do we know from observations? I only want to show you one example, which is from Sarafanov. This is around 60 north. It's here. Yeah. And around the 60 north, they took a desalinity distribution, and from the salinity distributions, you remember subtropical water is more saline, the subpolar gyre is fresh, so you can look for the biggest gradient, and if you do this, and then you put on the y-axis the longitude of the subpolar front, which you define by the salinity gradient in, I think, 2,050 meters depth. And on the x-axis, you put the mean winter NAO index, but not at the year you do the measurements, but you take the 5 preceding years by thinking that it will take a while until the circulation responds to an NAO. And then you come up with that if you have really high NAO, the longitude is 32 west, and if you have very, very low, it's 37 west. So there is about a change of about 5 degrees in longitude. There was recently a paper by Chaudhuri et al. In JPO, where they also look for the connections between the subpolar gyre and the inflow of this warm water, and they also get another player in, which was not in the previous figures. Let's say if you have a high NAO state, you have, of course, this is here the subpolar gyre water, which we have seen before, also enters the eastern Atlantic, and you have the gyre. And in the NAO state, also in this model, the gyre was reduced, and there was also reduced inflow of the subtropical water, but then the Mediterranean water flowed in. Does this have an effect on the AMOC? We know that this is also the high-resolution model run in Kiel, and and what they did here is it's as the ORCA model. They take only the climatological wind stress, so this is the same every year, but the only variability is then in the heat and the freshwater fluxes. And on the upper part, you see here the formation rate of Labrador seawater. Yeah, and you see when there is this reddish, there is a phase with Here you have you see that there are higher formation rates, and if you then, this figure shows you from 50 north to 10 north anomalies in the MOC. And you see that after formation of more Labrador seawater than normal, then you have anomalies propagating very fast to the south, and these anomalies are in the order of 2 Sverdrup. So from these, let's say, 18 to 20 Sverdrup of the MOC, you have about 10% variability in this model from the Labrador seawater formation rate changes. So it's about 2 Sverdrup at 40 north, and I don't want to show that here, but there's also a paper by Latif et al. Who looked at the density differences in the overflow waters and how this might affect the AMOC, and he also get another 1 or 2 Sverdrups. It's probably not as easy how the NAO affects the gyre, the subpolar gyre, and the AMOC, and that there also is an interplay between them that changes with time. There was studied by Katja Lohmann et al. And this is the NAO plus state. So they have a very long time, that's about 10 years or so, they really have NAO, a very high NAO in their model. And what is shown that in the first years, there is this is negative, means the gyre strengthens. So if you have a high NAO, you have a strengthening of the subpolar gyre, which in this model also makes a lot of cold water, and it also strengthens the AMOC. But if the AMOC strengthens, then there also begins to flow more subtropical gyre water, warm and saline water into the subpolar North Atlantic, counteracting the buoyancy flux caused by the high NAO. So after about 10 years, the gyre strengthens again. The gyre weakens, it gets more reddish, and it's by this inflow. So the strong AMOC forces then the gyre to weaken. And this is a different answer if you have negative NAO. If you have negative NAO, it just the gyre is weakening and continues to weaken even if you have that state for a longer time. Wow. What are the transports in the subpolar gyre? I want to present you some measurements we did across the Mid-Atlantic Ridge, where we moored pies. These are inverted echo sounders with a pressure sensor from 2006 to 2015. They will be there until 2015, we hope. But at the moment, of course, we only have the measurements till now. The pies, what they do, in short, they measure first the acoustic travel time, and from top to bottom and back, from bottom to top and back, and back to the bottom. And they also measure the bottom pressure sensor with a high precision parascientific sensor. And from the one, we calculate the transport relative to some reference level, which here we choose to be 3,400 dBAR because it's well below the Mid-Atlantic Ridge, and it's the deepest common depth of all our instruments. But to transfer acoustic travel time in something like a geopotential anomaly, or here, or let's say to make it easier, to infer it in TS profiles, we need Argo and CTD data. And these are the ones here. The red is the Argo, and the yellowish is the CTD data we used for that. So we get a sort of a lookup table. Yeah? And for a specific travel time, we have a specific TS profile, but of course we look for the geopotential anomaly. And from the bottom pressure, we get the transport variability at that depth, but we don't get the absolute transport because although these pressure sensors are very high precision, they drift with time, and we have to remove the drift, so we remove the mean. And this is the results. This is by Achim Rösler, and he is working on it's an update from something from the paper we published last year. So it starts in 2006, goes to 2010. And the reddish curve, that is the transport relative to our reference level. And the bluish, this is the transport variability in the reference level. And the black curve is everything together. And you result in about 30 Sverdrup, all in all. And from these 30 Sverdrup, 20 are NAC and 10 is Labrador seawater. And you see that there are some gaps which are filled with different colors. The gaps, this is the total transport from 47 north to 53 north. And we had some loss of instruments, and we somehow have to fill that in. So we took the relative transports. Yeah? So the transports to the reference level, we could infer, after knowing these transfer functions, we could infer them from the altimeter data. Because we could look, this is what it shows here, is the relative transport to the, this is the transport to the, relative to the reference level, to the, and this is the surface velocity, either inferred from the pies, or in bluish, the points are from altimetry. And you see that there is a very high correlations. So we can use altimetry to infer, to fill the gaps we have here in the instruments. And, but if we want to do that for the barotropic variability, which we see in the reference level, to see that it's not possible because the altimeter does not see these pressure differences. They are too small. But we can use those, very high correlation to take now the altimeter data and just and transfer these surface velocities into transports. Yeah, so this is the transport across the Mid-Atlantic Ridge from 47 north to 53 north from 1992 to present. That's what we have, and it's inferred from this correlation between the surface velocity of the altimeters and the transfer from pies, which in the time when we have pies is about 0.74 correlation. So. And if you look for the whole, it's about 27, so it's also about 30 Sverdrup. And of course, the same part as before would be Labrador seawater. Has this something to do, these changes, I think it's seen here better. Yeah, so in the maximum we have about 40 Sverdrup, and in the minimum it's less, it's about 10. Yeah? And if you look, if this has something to do with the NAO, this is the NAO index I showed you before. The correlation might not be that good, but it seems that there is some hint that in times when we don't have so much, when the NAO is more minus, no, the transport is not as high as when it's higher, when the NAO is more positive. We can also see that there might be problems also with even the time periods we have now. So in red, this is the this barotropic variability in the reference level. And you see here most of the energy is in about a maximum of 10 days. So these are these short-term part. But if you look for this transport relative to 3,400 dBAR, you see that there is a high energy in the range between 200 and 300 meters, 320 days. So that means that even annual means are biased by all these eddies and shifting of the pathways and everything else. So that even annual means are biased by could be biased by local variability of eddies and meanders. So now, okay, we had those 30 Sverdrups flowing in here, 20 NAC, 10 Sverdrups of Labrador seawater, and now we are looking, the next step would be to see what's here in the western boundary current, and then we will see what's in the Neufundland basin. So that is the mooring array at 47 north, so here is Newfoundland, and these are the moorings we have out now since 2009. And this is the snapshot of the lowered ADCP data behind. And I just want to show you the deep water export curves, transports. So this is year number 1, this is year number 2. And in mean, it's about 19 Sverdrup. Yeah, it's the same as with about plus minus 5. And so this is black. This is for the first year we did it, just summing up all the current meters. And for the second part, this was a little bit more difficult because we lost one mooring, which was very unfortunate. But we have redundancy in our system because we know it's a very difficult area and with very strong currents. So we could reconstruct the transport from the correlations we found in the first year to also infer the transport in the second year. If we now go from 53 north, that is at the exit of the Labrador Sea, there is a mooring array by Jürgen Fischer and his colleagues in Geomar. And there, the mooring array mean over several years is about 30 Sverdrup. That's the deep western boundary current. When we now go to 47 north, we have about 19 Sverdrup. If we go to 42 north, there was an array first by Bio and then also by EFM Geomar. There were papers by Schott et al. They end up with 11 Sverdrup. And if we now go even further north, south, that is at line W, Afotal, there is also now, I think, 4 years of data. He got John Toole and his colleagues, and they get a transport of 29 Sverdrup. So it seems we have high transports in the Labrador Sea, and we have high transports when we leave the subpolar gyre, but in the area when the North Atlantic current hugs the deep western boundary current, the transports are smaller. Another issue, you only see now the spectrum of the first day. Of the first year, not of both. But, this is also, it's a sort of energy. So the black is the meridional velocity. So this is a long stream. And the red is the zonal velocity, which is cross stream. And you see both have maxima here between 7 and 10 days. So we think this is the interaction with the NAC and the deep western boundary current just moving and meandering. But these about 15 to 30 days, there is only energy in the alongshore velocity. And this is something similar also, also Schott et al. Found at 42 north, but these periods were slightly longer than Jürgen Fischer and his colleagues found at 53 north. And Jürgen Fischer is compiling and using all the spectra, not only from the keel, but also from ours and other moorings to find out what these shifts are meaning and where do they come from. So now, let's go to the Newfoundland Basin interior. Interiors, as Harry Bryden told you, also are usually messy and difficult to measure. What you see here is a mean of 6 lowered ADCP sections, and in the upper part also vessel-mounted ADCPs. And this is centimeters per second. So here is Flemish Cap, and here is the Mid-Atlantic Ridge. And you see that this is the mean velocity, and the mean it's about here 10 Sverdrup, 20 Sverdrups, and even 10 Sverdrups here. This is the deep western boundary current, which we have about 15 Sverdrups here in total. And the next here, this is the North Atlantic current flowing in, and it's not only, these are the density lines, so everything below here is deep water and everything above is NIC. It's the North Atlantic current, but the velocity field just extends over the whole area until the bottom. And then there is a recirculation, so this is flowing south with same velocities almost as the inflow. And then there is some minor circulation going on, which is negligible compared to what you see here. So if we now look at the inflow here, in total, we have about 90 Sverdrup flowing in. And from these 90 Sverdrup, which is a lot, are 40 Sverdrup North Atlantic current and 50 Sverdrup is deep water. And we know we have about 19 Sverdrup in the deep western boundary current flowing out. We have another 15 Sverdrup just flowing in. And by the recirculation of the outflow, we have 60 Sverdrup flowing out again here, and therefore are 20 Sverdrup North Atlantic current and 40 Sverdrup are deep water. So if these all would have the same, let's say, features or characteristics, it would just be something let's say for us as water mass people from minor interest. But what is shown here is these are mean TS profiles compiled from all 6 sections. And from all sections, usually several CTD profiles go in that. So this is about, I think, almost 30 or 40 of those CTDs profiles went in there. So this, and I only show you now the deep water. So this is Labrador seawater, the upper part, the lower part, and this is what Harry said, it's Iceland, Scotland overflow water. There's a different name for the same stuff, and this is the overflow water. And in the western boundary, the outflow in the western boundary, it's very fresh. And in both Labrador sea waters and also fresher here in the Iceland, Scotland overflow water. The reddish curve is the characteristic of the water which flows in. So that's saline and it's also warmer, and that's what we expect. But the water which flows out is fresher and also colder than the water which flows in. So that means also part, at least a fraction of this newly formed water is also leaving the Newfoundland basin in the interior. So there are interior pathways for relatively fresher water and therefore younger water. So this is just an order of magnitude crude transports numbers which I compiled here. So here from Jürgen Fischer and colleagues, we have about 30 Sverdrup, which flows at the exit of the Labrador Sea. We have about 20 Sverdrup of that flowing out. We have about 50 Sverdrup of deep water flowing in and 40 Sverdrup flowing out again, and we have 10 Sverdrup Labrador seawater crossing the Mid-Atlantic Ridge. And of course, if you add up together, it's not zero, which is not as surprising because we are still missing some transport through the Flemish Pass, which we will know in the next years. And we also miss, of course, what's happening here by flow into the Irminger Basin. It looks almost perfect, but of course, this is just a preliminary. We have an inflow of 40 Sverdrup here of NAC. We have an outflow of 20, and we find 20 Sverdrup of NAC flow crossing the Mid-Atlantic Ridge. So that seems, at the moment, seems to be okay. And of course, we really don't know how much of this 40 Sverdrups flowing in. If there is really, is there a small recirculation? Are these 40 Sverdrups really going farther into the Newfoundland Basin and in the southern part of the Labrador Sea into the northwest corner, or is the northwest corner just 20 Sverdrup as the flow which goes across the Mid-Atlantic Ridge? This is just a very qualitative measurement, and this is the mean SSH you get out of Aviso when reference to the geoid they are using. Of course, we all know how difficult it is that the geoid is correct. So I just want to show that as a sort of a qualitative way. And some of the features we know. So this is the Mun eddy, which is at about 42 north. And we know that here the North Atlantic current flowing in is also about 90 Sverdrup or so. And then we have the Mun eddy with another, maybe also 90 Sverdrup or so circulating. And it seems that there is also some sort of an eddy sitting where we have our measurements. So with 40 Sverdrup, with also a lot of Sverdrup, let's say 40 Sverdrup flowing in and some of it flowing out. But and it seems, but of course from this we cannot be sure we cannot use it at the moment quantitatively to find out if that is compatible to these shipboard measurements. But we will find out later, because we plan and have submitted proposals to put in also pies here, inverted, that are also these inverted echo sounders with bottom pressure sensor, which will give us time series, which will be, of course, better than having just the snapshots. But if you compare that with model results from the flame, it's also, they have the same features. And one idea why these bands are always locked. So if I would show you the individual results, they would always look the same. So I think they are locked because of topography. Yeah? So this North Atlantic current, it just doesn't want to stay where it is. It wants to flow back, but it can only fly back as long as the bottom is not changing, because and so these bands are somehow fixed, and it makes it much easier to measure them. So the next and last part of my talk will deal about what is the fate of this new water, of this young water. What happens if it leaves, when it leaves the subpolar gyre? So what we do is we take all CFC data which has ever been sampled between 65 north and 20 south. And we take them from GLODAP, CARINA, and also by personal phoning all these PIs about releasing the measurements, and we get about 20,000 measurements in the water masses we are interested in. That means in the Labrador seawater and in the Denmark Strait overflow water on about 3,700 locations. So, you know, the problem with transient tracers is that the concentration which is measured depends on the year you sample. So I can't show you CFC concentrations because it would be dependent on the year of measurements. So what we did is we calculate parameters which are independent of the sampling date. It means they are independent of the sampling date as long as the ocean is not changing. Yeah? And these parameters are age and the fraction of young water. The subpolar region we know for sure is changing on these timescales. So here we are also comfortably off because we have a lot of data. So we only choose data where we have the most coverage. So we use data between 1996 and 1999. And we use then these data and produce maps of ages and fractions of young water. So what is young water? We had two water masses. I show you one, it's the Denmark Strait overflow water, which we know is formed in the Nordic seas, but we don't have data there. We didn't look at that. We just say we take the Denmark Strait overflow water after it has flown through the Denmark Strait and was descending at depth and is at the bottom. And we have Labrador seawater, which we say is there about 55 north, which is formed there, and when it enters the area here, we say it has been produced. There is an incentive why I will show you fractions of Labrador seawater and Denmark Strait overflow water which are younger than 40 years. The reason for that is that we would like to have the fraction as a proxy that shows us is the deep western boundary current exchanging with the ocean interior or not. And what is shown here is an age spectrum, but not at the formation area, but at equator of Brazil at about 44 west. And this age spectra, it's calculated with different Mots-clés numbers, and it's also shown here with, that means that different diffusivities here. And the black one, this is one with about, which we think is the most common. And here is the age. So you see the mean age at the equator is about 20 years. But depending on the diffusivities, even 40 years, you have some fractions. So if I always now show you fractions which are of the water which is younger than 40 years, we should assume if there is no exchange between the boundary current and the interior, this fraction should always remain the same along the boundary current. And if I would show you this for near the formation area, this would just switch to younger years. Now it starts here with 10, so it would be more like here. Yeah? But so we should be on the very safe side. So, but before I show you the fraction, I show the age of the young water. So this is the coverage we had with the paper which was led by Lebel. Where we took the WOS area data and get inventories and formation rates. And this is the coverage we have used here. And we start here in the Labrador Sea, and here is this is the age So of course it's youngest in the Labrador Sea because young means it had contact with the surface, so it has to be youngest where it's formed. And this very reddish colors, you see there is an inflow in the Erminger Basin, there is this part into the Eastern Atlantic which we know of. But also if you now leave the subpolar gyre and go further to the south, you see there is also these high reddish colors remain in the boundary current, although the gradient here is not that great, but it's still in the boundary current. But you also see that here are some hints that there are also interior pathways crossing from the subpolar into the subtropical gyre. I have to give you one caution. There were some of the areas like here and also here where we have multiple of data. So what you see here at age is really a mean over several repeats. But of course there are other areas where we probably only have one section. So it's just what we have measured at one time. So it's not as we really don't know if it's representative. We just put everything together. And we also know that we have other hints that there are interior pathways. So just keep it like that. And if we go then into the subtropical gyre and the tropical part, they are the lowest age, so the youngest water is always found in the western boundary current. It changes at the equator because there are these zonal pathways of North Atlantic deep water from the boundary current to the east and back, and this of course is also shown in these ages. But if we are south of this of those zonal circulation bands, which are located, let's say, from about 2 degrees north to 5 degrees south or so, the youngest water is still in the western boundary current. And this is the figure I've shown you before. This is the age of young Labrador seawater, and this is the age of Denmark Strait overflow water. And just by looking at those two figures, you see the biggest difference is that all this reddish is more confined to the western basin, and the reason for that is that it's so deep that it's below the mid-Atlantic ridge it cannot cross. So all this reddish you see here, this is not Denmark Strait overflow water, but this is the signal of the Iceland-Scotland overflow water, but which also then crosses, most of it crosses through the Gibbs fracture zone into the west and is somehow intermingled here. And if you now go further to the south, it just sticks to the boundary current. So it seems to be much more topographically confined, but which is also reasonable because we know where it's found at the bottom. So to summarize that is that we have those two water masses. The ages are usually younger in the deep western boundary current, especially south of the subpolar gyre. So spreading out of the subpolar gyre into the subtropics and the tropical Atlantic, the deep western boundary current is the spreading pathway. But when you look at these age gradients north of 35 north, so north of 35 north, and if we look south of it, we see that here the age gradients are higher. So we assume, and we also know from other indications, like from floats, which I have shown you in the beginning, and also by floats, by Rifos floats, which have been published by Amy Bauer and colleagues, that there are interior pathways between the subpolar North Atlantic and the subtropical gyre. And which is not much surprising. The Denmark Strait overflow water is much more confined to the western boundary than the Labrador seawater. And now I'll show you the fraction of those two. So this is the fraction of young water and the fraction of Denmark Strait overflow water. And what you see at one glance, there is no way the fraction in the western boundary current stays constant. It's decreasing. Yeah. So that means there is always and everywhere there is exchange between the deep western boundary current and the interior of the ocean, which is also not surprising. You remember Harry Bryden's recirculation schemes, and we know there is interaction, there is pulsing, there is meandering, so there is always exchange. And in fraction and in age, there is the same figure that the Denmark Strait overflow water, the higher fractions are more confined to the boundary, like the Labrador seawater, which at least in the subpolar North Atlantic can spread more easily to the east. So also the fraction of those two are usually higher in the deep western boundary current than the interior, and the fraction decreases downstream. That means there's always an exchange with the ocean interior. I now will show you in the next slide fractions along the pathway of the deep western boundary current. So, and we will now separate. In the next figure, you will see 5 areas, so 5 regions. The first is the formation area in the Labrador Sea, then the Newfoundland Basin, something which we call a recirculation zone, and we will see that in a moment. And then there will be the subtropical, tropical, and part in the South Atlantic, a tropical zone. So this is along the western boundary current. So this is 55 north. Yeah. This is region 1, Labrador Sea. This is the Newfoundland Basin. This is the recirculation zone. This is the subtropical, and this is the tropical part. And you see here the latitude of it. So this is 55 north. Yeah, then 42 north. This is at the southern tail of Grand Banks. There, I will not have time to show that, but there is John Toole's measurements. Here is line W. Then here is 24 north, 60 north, equator, and so on and so forth. And this is the fraction of this young North Atlantic deep water. Red is Labrador seawater, and blue is Denmark Strait overflow water. And it's, you see that for the Labrador seawater, it's 100% in the formation area. But Denmark Strait overflow water comes from farther in the Irminger Sea, so there was still some, they have been already mixed when we get to the starting point here, so we start with 90%. Then within the Labrador Sea, not much happens. And it's clear, even if there is an exchange, it is encountering water with almost the same characteristics, so it can't change very much. But then you have this very, very steep decrease of the fraction. Yeah? And we know the reason of that. That is where the deep western boundary current encounters the North Atlantic current, which brings in a very old and therefore CFC, less CFC and an older age of deep water, which comes in contact with the deep western boundary current, and there is this exchange which leads to this decreasing. And then there is the region number 3 where the gradient is much smaller, and then it just we just got over those regional wiggles, which some of them we had already explained in papers until the South Atlantic. So I already have talked about these largest along-stream age and fraction gradients in the Newfoundland Basin. This is the east encounter with the North Atlantic current water. It's not the North Atlantic, but it's the water below the North Atlantic, the deep water. And we also see these small gradients in the Labrador Sea, which I also have explained. And now we will go to the last point into this recirculation zone. This is here. We already know that there are deep recirculation. These were papers first published by Hogg et al., and there's also one by Smethy. And they, from current meter measurements and also measurements of tracers and hydrography and oxygen and so on and so forth, they found out that in this area here, the deep western boundary current and this recirculation zone are intermingled, and they exchange water much easily along, now it's out, and along the pathway. So here the gradients are somehow smoothed out. So I showed you that usually it's a good idea to go where the big signal is, but I also showed you that because the subpolar North Atlantic is sensitive to changes in the atmosphere, of course we also have a lot of variability, which is natural, and at the moment I think it's as likely as not, as an IPCC speech, if the anthropogenic impact on NAO is there or not. So if NAO even is changing, which we know makes a lot of variability in the subpolar North Atlantic. But we have started now with time series, and they are in key region of this subpolar part, and they are emergent. I've shown you, which is new, that we have this intense circulation in the interior of the Newfoundland Basin, and that there happens this mixing between old and young water, which also is an export pathway for deep water out of the western subpolar gyre. And I've shown you that the deep western boundary current is continuously and transporting young water, and this continuously is in the Lagrangian, also in the Eulerian way of view, because something which you have mixed in the interior cannot demix at the boundary current. So it has to be always, the highest signal is always at the boundary current, so it means it has to be continuing. If you look for future measurements, this is a line which crosses the Labrador Sea and also crosses the Atlantic. This is a joint proposal from US, UK, Canada, Netherlands, and the GEOMA, and it is called OSNAP, and it will be resubmitted, I think, from the US part in summer this year, and I think UK will submit it in beginning of 2013. Part of it is already in the water. That is this boundary current array at 53 north here, which I have also shown you some results, which have been published by Jürgen Fischer. And I think this Alert line, this is also the UK part where gliders are going, I think, almost continuously. So this is also in place and working. We got funding that was Dagmar Kieke together with Kerstin Jochumsen from Hamburg, and they get funding to measure the flow of Labrador seawater and deep water through the Flemish Pass. We will now in 2012 put the moorings in place, and the funding is funded till 2015. And we also have, we will now recover all these moorings and put them back, and also put the third one back. The university gave the funding to replace the mooring we lost. And these yellow dots, these are these inverted echo sounders, which are already in the water or will be placed. Funding, of course, needs for that. And we submitted it to 2015, but we are still waiting if it will be funded. But we have ship time for 2012 and 2013, which is shown here. In 2012, we have a cruise servicing our moorings and pies, and do some also tracer measurements, but not much. But we also will join the cruise by our Spanish colleagues, which is led by Aida Rios, which will cover the French Ovid line and also the AR7 in the west, and we will take CFC samples there. In 2013, we got ship time funded for a cruise which covers not the whole, but an important part of the Western Basin. And for 2014, we submitted, and leg 1, which means the oceanographic part, was funded. But what you see here is also these greenish dots. These are sediment cores, which we would like to take, so that we will get some sort of a means that we hope where we can extend the time series we have with recent data more into the past by high-resolution sediment cores. But high resolution in areas with a lot of currents is not very, it's difficult, but maybe there is an area here at the Orphan Knoll where we get more sediments, and we also at the Laurentian fan, we hope that we get some that we can get sediment cores, which will help us in prolonging our time series into the past. Before closing, I want to make 2 announcements. The first is, if you are in Vienna and you are interested in the North Atlantic, there is the whole Thursday you get talks about that topic, and on Friday you will have the posters on Friday morning. And please keep in your calendar that there will be a North Atlantic session in the IUGG meeting, which will be next year in July in Göteborg. And you see the conveners of the sessions, which will really encompass a lot of the topics we also have seen here, but also probably more. We'll go more into in the recent findings. Thank you very much.